Okay, good. Sorry, guys. Right, so we move on now. We go on to the next technique, range Doppler. As I said before, this is just let's say an extension of what we've seen before, and what we named coherent integration technique. So the idea, okay, is now to sort of form an image, not really strip by strip, but in blocks. To build an image in blocks, now we are collecting more samples than before. When I say more samples than before, it means now I will allow my buffer, my value, number of pulses that I record and I keep in storage, to be longer in terms of time here. So my observation time becomes, let's say, larger, or even much larger, then let's say the ratio between the footprint and the velocity. So compared to what we had before, okay, the T-ops would have been only this bit here, so that we have another, okay, another beam width exactly starting from here and finishing here. So now we continuously sort of sending out pulses and receiving, which was exactly what it was happening before, but now we look at this problem and trying to form an image of all this area here, okay, in one go, not in strips. So to do that, we are considering exactly the same signal model. So nothing changes from that perspective. So we're now assuming that we have a number of scatterers within this region that we call LS. Okay? So all these scatterers here that are contained in this region here are all illuminated, okay, for the same amount of time. And the amount of time they're illuminated for, let's call it T, is the time that it takes for the platform to move from this point, for example, this here, all the way up here, so that then this point here is not illuminated any longer after. So if we consider all these points here, they're all illuminated exactly for the same time. Points that are sitting inside this area here, the extra L here and here, they will be illuminated only for part of their time. So they will be partially illuminated. Okay, so these are called in-scene scatterers, whereas these are partially in-scene scatterers. And the scatterers that will be sitting outside here, they will be out of scene, okay? They wouldn't be illuminated at all. So we don't have to consider them, of course. So in terms of Doppler frequency, nothing changes. So we have exactly the same expression that we had before for the point O in the middle, okay? So this is exactly the same form. We don't have to derive it again because we derived it before. For any other scatterers here, in-scene scatterers, okay, we get an expression that is exactly equivalent to this one, but with a shift that depends on the position of the scatterer, which is exactly what we had before. Now, the rectangular function, as you can see, it's got the same length as the other. So the difference with what we had before is that this term here was actually limited by a value here, which we call delta, that was smaller than L. But now all these scatterers here are actually illuminated for the same amount of time. Okay. And the dwell time, the illumination time, okay, is L over V. So if we want to write this in terms of time rather than space, then you would have to use dwell time as the illumination time. So in terms of how these Doppler frequencies actually look like, right? Well, there's not much difference with what was happening before. We're just extending, okay, the observation time, and we are allowing for many more scatterers now to be fully illuminated by the antenna, by the radar, okay, so that we have from this point, actually from this point here to this point here, which actually is the LS that we had before here. The in-scene scatterers are all inside this area here, and they all generate full expressions of this frequency here. So this frequency behavior, again, is a linearly decreasing frequency, and all scatterers produce exactly the same behavior, but each of those are located at different positions in space and in time. Those red ones here will be the scatterers that sit inside here or here. The one on the right will be these ones here. The one on the left will be these ones here. So they are partially illuminated. So they don't produce full response in terms of frequency. So there's nothing really new with respect to what we had before. Now, if we perform motion compensation now, what's going to happen? Nothing different from what happened before. Now, each scatterer will be left with a constant Doppler, which is proportional to the position that they're occupying in the scene, x sub k. And they, for the in-scene scatterers, they are illuminated for the whole entire time, which is in terms of space, for the entire synthetic aperture, which is L. If we look at this, this represents pretty much the contributions from different scatterers, okay? And as you can see, each of those have a duration equal to L, or if you want T ops, okay, which is equal to L divided by 2, divided by V. And they are shifted in sort of time duration, because they start later and finish later, or start earlier and finish earlier, okay? And they are shifted in Doppler because of this position here. So this slope here, okay, depends on the velocity of the platform. So the faster the velocity, the more steep this slope will be. And you get to a point where you get a maximum frequency up here, okay, for the scatter that sits right at the border, this one here and this one here. Oops. They generate this maximum and this minimum frequency. And these are the partially in-scene scatterers that do not produce full-blown Doppler frequency. Well, if you calculate now these maximum values here, okay, this and that, they increase value with respect to what we had before, because now we are allowing for more and more Doppler frequencies to be in scene. And this depends on the value LS. So the larger, okay, we choose this area to be, the higher the Doppler frequency that we're going to obtain. So the bandwidth of this signal here, okay, is different from the bandwidth of this signal here. Because this signal, which is the received signal, this bandwidth here is always contained between V ds and minus V here. Because that's how physically the Doppler frequency is generated by the motion platform motion, which induces that Doppler frequency. So the bandwidth of the received signal is this. So our PRF, okay, has to be set so that this is maintained. In terms of this signal here now the bandwidth of this signal is actually enlarged. So once you multiply your signal, okay, times this new factor, then you need, okay, a wider bandwidth to represent this signal. And that is because you're multiplying a signal by some modulation function, which is that phase term that is associated with one point. This is a modulation function. When you take one signal and you modulate it, its bandwidth changes. So there's no, let's say, there's no wonder if this bandwidth here, which is from 0 to here, is actually increased. Okay? So the representation of the signal that you capture, that you collect with your data, all right? That particular signal has got this bandwidth. But any processing that we do afterwards needs to be dealt with by considering this bandwidth here. So we have to be careful. We'll go back to that. For now, let's notice that this is actually different from the other. Okay. Right, so some of these remarks probably made them already. Let's read them aloud. Anyway, the signal contribution of the in-scene scatterers are pure tone or length, dwell time, which is L divided by V. And these are the pure tones, because now these signals exist for a certain amount of time. So when I say pure tones, they're not pure because they're time limited, but they're pure in the sense that the frequency at which they oscillate is constant. So any scatterers within the scene produces a constant Doppler, okay, signal, so an oscillation with a constant Doppler value, and the duration is fixed and is equal to dwell time. The Doppler frequency is proportional to the scattering azimuth position. That's another important thing. We have a direct relationship, okay, between the position of the scatter and a Doppler that it generates. We have to remember this, because this is going to lead us later to understanding how to form an image. Okay, the bandwidth here, okay, is actually this minus this divided by 2, which is actually just this. Okay? And this is you can calculate it, and all right, and it can easily demonstrate that this bandwidth here is greater than the bandwidth, Doppler bandwidth of your received signal, which is this one. When Ls is equal to 0, these two are actually equivalent. Let's look at a Doppler analysis of this signal. Let's say our signal now is a composition of all these terms. Okay? I can read my compensated signal as a sum of a number of oscillations. And each of these oscillations, okay, occur at a given Doppler frequency that is generated by these scatterers, and I have a composition of those. If I want to write this down, okay, I would say that my received signal, after compensation, is the sum, actually let's put 0 as well, of components that are sigma I, okay, e to the minus j 2 pi f di t. This is how it looks like. A sum of oscillations, complex oscillations, and each of those oscillate at a different frequency. This particular different frequency is associated with the position of a scatterer. And we have it here. Each Doppler frequency depends on the position of the scatterer, which is x. When x is 0, this is 0. When x is 1, well, this would be 2v. So if I look at the spectrum of this signal, what would I expect? I would expect to see sinc-like functions. If I Fourier transform that, I get a sum of sinc-like functions, because these are, I didn't write it here, but there's a rectangular function there. Let me write it. T12. So that T12 here will be the first zero, okay? Yeah. So that tells me about the resolution. So if I have scalars that are at a distance that is at least, okay, this much, then I will see them separated. Right. So this tells me that what I'm seeing here is pretty much, okay, a Doppler profile of my signal in a particular range cell. But I told you before that this frequency f is actually related to x. So this is scaling factor. That means that I can invert that equation and rescale these x's into x. And what's x? It's my azimuth. So that means that this is actually my profile along the azimuth. And if I can do this for this range cell, and I can do it for the next range cell, and so on and so forth, then I can form my psi image, okay, in this way. So these are sinc functions. I know what the resolution is, and this is good for all the in-scene scatterers. For those who are sitting outside that area, I see again a sinc function, but this is different. It's lower, and it's wider. And why so? Well, this rectangular function here, all right, for this one, it's got a shorter time window. So the dwell time for those scalars that are sitting here is less. These are observed all at the same time as dwell time. But this one's here, no, because then I switch the radar off here. So that's why they appear like this. So those scalars are still visible. I'm not saying they're not. They're here, and they're also here. So if you form just a Doppler spectrum here, okay, you will see the scatterers in scene being focused really, sharp. And the ones at the border, you will see that as you move out towards the border from one point, certain point, all the way to the actual border, you will see things getting more and more blurred. The effect of blurring is simply because that function there becomes wider and wider. So you start losing resolution from here down to here. Resolution goes from this point to infinity. Infinity being like a, infinity y.
Do you usually filter those out? Or just...
Well, yes, that's what we do. We filter things down here. And we throw that out. I'm not sure you have to do that now. Well, it actually tells you here that this part here are discarded. The scatter located in plus minus ls divided by 2, which is the scatter is here. Okay, they're good in a sense that they are perfectly, say focused, and the point spread function here is pretty nice, same as this. But they suffer from side lobes from the ones on this side. Their side lobes become wider and wider as they move out. Okay? So that unfortunately spreads the energy here onto here. So it might happen that if you want to avoid those effects, you might actually cut your image even, considering a shorter window. And that's what it says here. So this suggests basically that what I have to do is compensate my signal, right? And then basically calculate the spectrum of this signal, which is, I can do it with an FFT. So it looks like I can obtain cross-range or azimuth profiles by using an FFT after compensation. So here, there are steps, the steps that I need to to form an image using the range Doppler technique. So for any range cell, I specifically looked at one, what I do, I store the azimuth samples for an observation time, t ops, and this contains ls plus L and divided by D, where ls is what I consider the in-scene scalars. So that's the extent of the image I'm going to obtain that I consider a good image. Right? The rest will be low resolution and I want to discard it. So I can make this as big as I want, but the bigger, the larger this number is, the more memory I will need here to store this, and the longer will be the FFT that then I have to calculate. So computationally, and in terms of memory buffer, things get worse and worse in the computational point. So this is the function that I use to form motion compensation with respect to this scene center O. Okay, that's the same that I was doing before. And then what I do, I take the FFT of the compensated signal. Instead of summing up this, okay, remember for the previous technique I just used a sum. Now I'm using an FFT, so that I'm actually forming the whole extent of the image along the azimuth for all those samples that I used. And then I remove the Doppler spectrum outside the interval that is indicated by LS. And those are the whole resolution bits that sit on the left and on the right. And then I scale the frequency axis according to the linear law that I've written here. So X now becomes a function of F, and this is the sort of proportional factor that you have to use to rescale that axis. So now what you obtain, if you go back here, if you scale this one in range, in azimuth, sorry, then you get a position of scalars along the azimuth. So this is how it works in terms of functional block scheme. So you get your IQ signal in here. This becomes your sort of matrix that gets updated in some way. I'll tell you in a minute. So this one basically stores all the samples for each range cell, but also in slow time. All right. So slow time in this case is all the samples along the aperture. And you get it for all the range cells. So these are range profile, okay, for the first sample, range profile for the second sample, so on and so forth. And then you work, in this direction here, because now each column here represents the time history for that particular range cell. And that means now you're focusing on one range cell and you're looking at all these samples that you are taking for that particular range cell. So in this case, they are put in columns here. And this, okay, it's got a length of n, where n is the number of samples that you have to process coherently. Okay, how do you get to n? If dwell time, t dwell, okay, is the amount of time that you coherently processing your signal. If you multiply that by PRF, or if you divide that by TR, you obtain a number of samples. So n is actually obtained in that way. So then you perform your motion compensation with this phase term here, and then you get another vector n, because this motion compensation is an element-wise multiplication. So you get a same vector n, and you call this, at this stage, you call this the compensated signal, okay, after this operation. And all your Dopplers now are all like this. And then you perform an FFT. So your model, your signal model at this point here is this. You take an FFT of that, okay, and you obtain those sinc functions. And that's your image. And then you display it. Yeah.
So is that motion compensation term equivalent to a matched filter as it's shown?
Only to one point.
To one point. Okay.
Now we're not looking at the whole imaging, the whole section. I haven't introduced all the limitations of this yet. But let's say that for for so small section this works. And we'll see then the limitation of this. But in theory, right, that's the way it should work. If you compensate with respect to that point, you get all those effects. Okay? Fine. So how do you now form, let's say, a psi image, okay, that can, in principle, be formed continuously, like in the case of the coherent interaction, right? So you want these strips to continue. Well, if you form one block here, first image you form, say, you start from here, finish here, collect all these samples for a particular range cell. These are your in-scene scatterers. You form an image of this, okay, which is full resolution. What happens at the next batch? See, you form an image actually that goes from here to here, but you throw out these terms here because they are not full resolution, and you remain with this image here. When you have to form this other image, which is the blue, you have to start from this point and continue this. See, there's an overlap between the first batch and the second one. So when you go here, when you update your matrix here, you don't throw out the whole matrix and replace it with a new one, but there's a bit down here, okay, that you keep, actually it's this way, that you keep because the last samples that you used for the previous image formation, you have to use as the first samples now, or the following one. So then now when you stitch up these two range Doppler images, they stitch up with no gaps and no overlap. Okay? So that's the way you pretty much update these things. Here are some examples of side-looking synthetic aperture radar. That's a suburban area. This actually should be a runaway of an airport. The same as here. This is Tyrrhenian. I think this is the northern part of Tuscany, and this is the sea, and there's some mountains. You can recognize some features. And this is another psi image of the ocean, where you can recognize a number of effects. There's a ship here. There's an noise leak here. Some windfalls. And you can pick up a number of features based on the contrast, as I was saying before. How do you see that this is a ship? Well, I know that it's a ship and it's not easy to see it, but you see this bright return from this small area here, okay? And if you zoom in, if you've got enough resolution, you can recognize the ship features. It's hard to recognize a windfall from a noise leak because they both decrease the reflectivity of the sea surface. A windfall, okay, is recognizable against, say, sea clutter when there's wind blowing, because the wind, when it blows over sea, it creates ripples. Now, these ripples usually are comparable in terms of wavelength with the wavelength of radar, okay? If you use a microwave type of radar like X-band or C-band, then your wavelength is a few centimeters, and those are the kind of same length of these ripples. So when these ripples become kind of periodic, then this periodicity actually add up coherently, and this phenomenon is called Bragg scattering phenomenon, and that increases the Bragg scattering. Yeah. Okay?
No, sorry.
Bragg. So when the wind sort of decreases and actually stops, you can see this ripple disappears from the sea surface, and that makes the sea surface smoother. So now the electromagnetic wave bounce on the surface and off the other way. They hardly come back. Whereas these ripples make the backscatter much stronger. Okay? So that's why you see this as a dark area, and this is not as dark and that's what happens here. Oil slicks, they produce, because of the oil on top, the viscosity of the oil is higher than that of water. So the wind doesn't produce the same ripple. Okay? If you try and look at an oil film on top of water, it kind of smooths down the ripples. And that's why it looks darker, same reason. So, hard to distinguish this from this. But for certain applications, when you look for oil slicks, for oil spills, then it's important to be able to do that. And there are techniques that allow you to actually distinguish this from the others. Typically, what we're trying to do is correlate the ship and the oil slick. So we're going to try and find them for what they've done. Can't dump oil in the ocean. It's big. Anyway, these are some interesting things, and you can see here again the dark area because of the tarmac. And you can see here, depending on the orientation of the face of the mountain, you can see bright and dark areas. That again is part of the scattering mechanisms. Anyway, we're gonna skip this for now. If there is time, we'll go back and go through it. It's very mathematical. It's a technique that is used for side looking SAR, and it allows to go beyond limitations that are actually well defined here for coherent processing and for integration and for range Doppler. So I'll go through this first, and then if there's time, we'll look at this as well. But just to give you some examples, it's quite mathematical, and it's interesting, but if there's time, we'll do it. So what I want to talk to you about now is SAR system design. So a lot of parameters that we looked at, okay, are somehow dependent on each other, and we can't arbitrarily choose those parameters and do whatever we want. You even played around a little bit in the code before, and you see that depending on how you choose your velocity, platform velocity, you have to accordingly choose the PRF to adjust things and make sure that you don't scramble things up. So, and even the antenna aperture and the distance, or the distance at which the platform flies with respect to the illuminated area, the swath, so on. So for all these parameters come into place here, and basically we have to understand what are the boundaries within which we can, tune our parameters so that we don't break assumptions, we don't break conditions that allow us to form SAR images effectively. So we will start with PRF constraints. Okay. So PRF has got a lower bound and an upper bound. The lower bound, so the minimum PRF that we want to use, okay, depends on the bandwidth of my received signal. If my received signal, I don't know why it's not here because I was here. There we go back, okay? So for the coherent integration technique, my PRF has to be, okay, greater than 2V over ds, because V over ds is the bandwidth of my baseband signal. So if I want to make sure that I sample my signal with a sufficient number of samples, and Nyquist tells me how to do it, which means at least twice as much as the signal bandwidth. So twice as much as the number 2. So the PRF has to be greater than that for the coherent integration technique. What I see here, this PRF here, okay, this is the equivalent PRF that I want to use. It's not necessarily the PRF that I use to sample my signal, because I can interpolate it later and obtain a higher PRF. But typically, what I'm dealing with is the compensated signal. So when I go and form my FFT of my compensated signal, right? I have to have enough samples to actually look at the spectrum where all my scalars are placed without any aliasing. Okay? So to do that, I really have to have a number of samples that is actually equal to this one. But the signal that I actually sample initially, all right, it's still got the same bandwidth. So my constraint, okay, can be relaxed to this one, provided that then I upsample my signal before I multiply it by that term, okay, which I indicated, maybe it's too many slides back now, as the phase term that is associated with the point O. So that's the minimum value of the PRF that I have to have to satisfy Nyquist privilege. But the upper bound for the PRF, why is there an upper bound for the PRF? Well, you're familiar with classical radar, you know? If you increase the PRF too much, what's going to happen? Your radar becomes range ambiguous. Right? Exactly. A SAR system, okay, makes use of radar, so it shouldn't be that different. I don't want to make my range ambiguous because then I'm going to fall back a lot of contribution. And they're all going to be folded on top of each other so that I can't recognize anything. So, as a first approach, okay, I should use, okay, the rule that tells me how to obtain a non-ambiguous radar. And that means that my maximum range here should be less than a non-ambiguous range, where the non-ambiguous range, okay, is defined by my PRF. So that tells me that the PRF should be less than or equal at most to C divided by 2 times Rn. So that tells me that, okay, here, okay, my non-ambiguous range is actually sitting here, if this is n equal, or is sitting further, if this is less than. That means that this is the last echo that I'm going to receive, because this is the antenna pattern. Anything outside this, I assume, is 0. So a scalar that sits down here will not be seen. That means the last echo that I'm going to receive is this one. So if my non-ambiguous range is down here, I don't risk anything because there's not going to be any echoes that's going to fold back. Okay? Are you familiar with non-ambiguous radar? Yeah. Well, I think we talked about it a little bit yesterday. You know, you got a transmitted pulse, okay? The non-ambiguous range, okay, if this is T, is also Ct divided by 2 becomes R. So that means this R here is what I call non-ambiguous range. And this is because if I send a pulse here, I may receive an echo down here. This echo will always be associated with this, but this echo may be as well generated by that pulse. But in that condition, I will never have an echo that it can be associated with that, because there's nothing but beyond that point. So if my Rn maximum range is here, it means that everything that I receive will be inside here, and then 0. So there's no risk that I get an echo of this transmitted pulse any later than this point. So that's the condition that I can apply, and if I apply these conditions, I'm damn sure that I'm never going to have, okay, second trace errors, and therefore ambiguous errors. Fair enough. When are we going to buy a license, eh? Oops. Right. So I can rewrite this. Okay, Rm can be written as h divided by the cosine of this angle. Okay, and that becomes Rn. Fine. I've got this in terms of, let's say, system parameters or geometry parameters, okay? And these are parameters that I can set when I, launch my mission. I say, okay, let's fly at this height, and let's look down with this angle here. And this is the elevation beam width. Fine. For spaceborne SAR, H is 800 kilometers. Let's say theta p is 20 degrees, theta elevation 10 degrees. Well, Rm is 882 kilometers. Well, in this case, the PRF should be less than 170 Hertz. 170 Hertz is a very small PRF. Now, let's not forget that PRF, okay, has to be greater than this value here. And we had an example before where this value was about 500. Right? It's 250 times 2 is 500 Hertz. So already, and imagine with a velocity of 7 k's per second, this would be even much worse. So for spaceborne SAR, you probably can't even find an intersection here that is non-zero. So this criterion here for spaceborne SAR is not really applicable. It may be applicable for airborne SAR, all right, because now if we fly at a height of 8 kilometers, which is already pretty high, usually we fly even less than that. Same sort of geometry in terms of antenna pointing, antenna beam width, right? So this means 8.82 kilometers. PRF less than 17 kilos, which is plenty. So for airborne SAR, fine, we can go with this approach, which is typical of normal radar, non-ambiguous distance. We make sure that Rm is less than an ambiguous distance. Perfect. For airborne SAR, it works. For spaceborne, it doesn't, because it's such a far distance that it becomes really an impossible task. So how are we going to do this? Spaceborne SAR exists and work, so there must be a way of doing this. Well, it's interesting to notice that for spaceborne SAR, it is true that you get your final, latest echo down here. But it's also true that the first echo that you receive is very close to there. Because now you're looking down, okay, from 700 kilometers, and you may be illuminating 100 kilometers of swath. The projector is maybe very small quantity. So that means that this is actually quite concentrated along this area. But there's nothing afterwards, but there's also nothing before. So you can keep on transmitting, okay, pulses before even this one comes back in. So this is an ambiguous radar, it is true. But am I interested really in measuring the distance of my objects from my platform? I know exactly when I'm flying. I know what the Earth is. With the orbit determination system that we go now for satellites, we know it by the meter. We got an accuracy of that position less than a meter. So I know exactly how many pulses there would be between here and there. I don't have a problem of measuring the distance of this object. I want to form an image of the ground, but I know exactly where the ground is. I can then overlap that, my SAR image with a Google map easily, because I know exactly where I'm flying, I know exactly what I'm looking at. Fine. So there's no need, okay, for me to measure that range. I can measure range inside here very accurately, but I know where my first return is going to be. So, okay, this is my 634 kilometers, okay, and then I move on from here. I already know where I am. Fine, so what I have to avoid then? I have to avoid that two echo supports here. When I say support, is the extension of the echo, okay, domain. So two adjacent support do not overlap. So that means that if red is my first, okay, let's say I'm labeling now my transmitted signal. First one I label it with red, second one with stripe or black stripes. So my echo relative to the first transmitted pulse is red, and the other one has got the same pattern. So I can see now if these two are too close, then these two echoes overlap. That's not good. So I have to avoid that for sure. So the first criterion that I want to use is non-overlapping echoes. So to make sure that those two echoes are non-overlapping, then I have to make sure that C over 2PRF is less or almost equal to the distance between this and that. So this support, let's call it delta R if you want. Okay, which is equal then to delta Y times sine of theta P, where delta Y is the slant range, or sorry, delta Y is a swap, it's a ground range. So this is a slant, okay, and this is the ground, which is here. So delta Y is the projected slant range. So this that is delta R, the blue one. Delta Y is the projected range onto the ground. So this is called slant range, this is called ground range. Okay. This condition by itself is not enough. I can make sure that this doesn't happen by applying this formula here, okay, which limits the PRF. But for sure, I have to make sure also that any of these echoes here do not overlap with the position of a transmitted signal. And why that? You can't receive when you transmit. Exactly. So not only I have to make sure that these two echoes are non-overlap, but I also have to add another condition where this doesn't overlap with the echo. It's almost like I can plot onto the ground this sort of black bands, right, that correspond to the transmitted signal as it travels. Right? So I have to make sure that my swath sits in between these two areas where you can't receive. So there will be that range where you can't receive because it's transmitting, and these are the range, and these two ranges here, okay, have to be placed so that one is before, one is after, and none is in between. Because as soon as it overlaps with the echo, it basically removes it. So you will see a blank in here and a blank in there, and you will receive the echo only in between, here, here, and a little bit there. And there will be black bands on the ground. So you form your SI image and you will see black bands because there's no signal received. So you're processing zeros very much. Fine, so this is the condition, okay, for this not to happen, but it's not enough. I say it's not applicable means it's not enough. So I have to make sure that I also avoid echoes superimposed to transmitted pulses. So that's the condition that I have to make sure of. That any transmitted pulse here on the same axis does not overlap with this. There's a third condition that I can apply, if I can. It's not strictly necessary, but it's actually a good condition. So when I look down on the ground with my antenna, okay, I look on a slant, right, with an angle, a pointing angle that is theta, that theta elevation, right? And that's fine. Now, I know that my real aperture will have side lobes itself. Particularly, there will be a side lobe that will point right at an idea. Now, that direction is particularly dangerous because then you get a really strong reflection, even from the surface. So even though there's a side lobe and there's not much energy going down and coming back, still the power that comes down from that sort of flat surface, upward reflection, is very strong. So you want to try and remove that. And what's the best way of doing that? Making sure that exactly at that distance, I put a transmitted pulse. So if I can put if I can sort of set the PRS so that exactly at that height, right, the distance where R is equal to H, I put a transmitted pulse that I basically know all the return from the ground and from the nadir. Okay, I'm doing it on purpose. What I have to avoid for the area where I'm interested in, then I have to actually try and do it for the nadir. So nadir will be a very strong signal that comes from another area that I'm not actually illuminating, and that will be a disturbance. I have to get rid of it. So if I can do that, then it's interesting because now I can make sure that that I can do that. Or the only conditions for which I can do this, right, is that I have a range ambiguity condition. So I have to be range ambiguous in order to be able to put a pulse right at that distance. But that's something that I would do for a spaceborne SAR. For an airborne SAR system, for which I'm not ambiguous, I can't do that. Because if I put a pulse there, that will be ambiguous also for the rest of the scene. So ambiguity buys you this possibility of placing a pulse directly at nadir. So imagine this is the nadir return. You put a pulse in there, and you know that. Okay. So this condition here, okay, is actually related to, let me see, so C over 2 PRF, fine, that should be less than Rn minus H, which is Rn minus H is this one. So I'm avoiding that this, okay, is overlapping with this. Right. So that's a condition that allows me to make sure that I don't have echoes superimposed to transmitted pulses. Plus, what I can do, I can choose, if this PRF, okay, right, PRF has to be less than this. If I have some lead, some way of moving my PRF between, let's say, this upper bound and the lower bound that I get from the Nyquist, okay, condition, then I can search whether within this minimum and maximum value of a PRF that I can actually choose, I'll go and check if I can find a multiple of the PRF so that I can know the nadir condition. So this condition here, see, where M is a generic, it's a number, right, that indicates the number of pulses that I have to wait for. So it could be the third, the fourth, the fifth, as long as there's one that covers that. And I have to search for that. So later we'll do a little bit of a sort of tutorial where we put numbers in it, and we'll check a condition for which the PRF that would be limited by a minimum and maximum value, okay, will search across that interval if there exists a PRF that is a multiple of this, so that then we can know the nadir. We can do that later, so it will be probably clearer. So then we come to this, okay? So basically, the PRF, okay, that we are considering, okay, has to be confined between a minimum value and a maximum value. For the non-ambiguous SAR, the maximum value with this would be this, and for the range ambiguous SAR, it becomes this one, so that we make sure that we have echoes between pulses. Okay? Of course, if we get echoes between pulses, then also the first condition is satisfied, because this one will be after the other. So this condition here, all right, becomes the condition that's most strict, and it's the one that we have to apply for range and radius. So for airborne, we can go with this. For spaceborne, we have to go with this. That doesn't mean that we can't use this one for airborne. We can do it as well. Okay? It's not necessary. Okay. Fine. So we talked about PRF constraints. Now we're gonna swap. Now we're gonna talk about the swap limit. We have this condition here, right? As I said before, the minimum and the maximum values, all right, have to be such that the minimum value is less than the maximum value. Otherwise, this becomes an empty set. When this value is greater than that, there's no PRF that can satisfy these conditions. So this poses a condition that says that this has to be less than that. Okay? And if you write down this condition here, and I think this has been written for the range Doppler technique, and the range ambiguous SAR is an example, okay? Then you have to force this to be less than that. And if you do that, okay, you end up with a condition on the swath, delta y, which becomes, okay, an upper bound, which tells you the maximum extent of your swath that you can tolerate. It means that if you make your swath any larger than that, you automatically will make this guy larger than this guy, and you will not have any chance to find a PRF that suits you. So this poses a limit on the swath, and you can sort of basically write this less, strictly less than that, or equal to that if you want. If you put it equal to that, you find the limit, okay? And then you solve for delta y, and you end up with this expression here. So if you put your numbers in there, you quickly realize how you end up with the conditions of your swath based on these parameters. It would be interesting to say how the swath, okay, and the resolution of your system are actually linked. We'll go back there later. But somehow, within these numbers here, okay, this is expressed in terms of system parameters. But if you rewrite this in terms of the system resolution, okay, you can derive from here, okay, then it's interesting to see that as soon as you push your azimuth resolution to be finer and finer, okay, and how do you do that with the SAR? You make your antenna smaller and smaller, okay? You can do it, but you get to a point where this number, okay, becomes smaller and smaller. And that means that now you're confining the swath to be smaller and smaller. So that means, okay, you want very high resolution in azimuth. Well, you can't observe more than X amount of swath. And I'll show you later some systems and how these systems have different modes with which they operate. And there are modes that have very high resolution, but they only can image small areas. Whereas if you want to image some vast areas, large areas, you have to reduce your resolution. And that's a trade-off you can't beat. Okay? So you want resolution, you reduce your swath. And it's, of course, everyone would like to have a very fine resolution but very wide swath, because at each passage of your platform, you would image a much wider area. So if you have to do whatever you want to do, you want to minimize the cost of flying something. If you want to do surveillance, or if you want to do remote sensing or whatever of a certain area that is maybe 1,000 kilometers long, and you only have 10 kilometer swath, where you have to fly 100 times to cover the whole area. And if you can have 100 kilometer swath, you only fly 10 times. If you have 500 kilometer swath, you only fly twice. So everyone would like to have even just one flight and cover the whole world. Of course, you can't do that, but the interesting thing is that the wider your swath becomes, the coarser your resolution in azimuth will be. So you've got some trade-off now. How much resolution do I need to accomplish my mission, to find out about what I want to find out? Okay? And how it trades off with how many times I have to fly before I cover all my area. Trade-off is there. We get back to the right a formula that comes with the resolution. Depth of focus. Okay, what's the depth? I said before, if we compensate for each range cell, right, we make sure that we do compensate for the motion of that point, okay, and reasonably for all of the amount of points that are nearby, okay, where you, with an FFT, for example, in a range Doppler technique, in FFT, you can focus at the same way a number of scatterers, okay, that are sitting on the same range cell. So what we are trying to see here is that, okay, can I use, okay, the same range, the same point O on one particular range cell to focus also the range cells nearby? Or to say it with better words, if I focus towards that point, how deep is my region where I can still focus, okay, compensate, let's say, okay, with the same phase term? So it's like if you have a camera, right? If you have a camera and you zoom in and out, and then you focus with your lenses, right? Even there's a depth of focus, right? Because you're now compensating with your lens for the effects with respect to one point, and this compensation will work for certain points further. I have certain points, just before them. The same thing happens here. With the same phase term, how much can I compensate in range? Because that will save me computational burden, right? I can just use one simple form to compensate for many range cells. So if I do that, okay, I choose a point P, maybe in the middle of the scene, and I compensate with this term here. Now, how am I going to say if things work or not? Well, that will depend on how accurate this phase term is when you match it with the real phase term. So what you do, you basically go and calculate the difference between this phase term here, okay, the one that you would have to compensate for the ith range cell, and the one at P. So when I is equal to this point here, of course, this comes to 0, right? But as soon as this range here gets further and further away from RP, then you get this number, okay, which is a phase term that is actually increasing. So where's the limit? Well, the limit, I can pose it, right? I can choose as a limit pi divided by 2. If I want to be more strict, I can choose pi divided by 4. So I pose a limit in my phase rotation, because that phase rotation represents an error that I add to my coherent processing. You remember when I said, once I compensate my motion, that point O, it's got all the phases aligned. So what happens if I don't compensate right? There's these phases that don't align anymore that much. There will be an error. That will curve this. So that means that my integration will be less. How much can I tolerate? Well, that will depend on how much I can tolerate this. And the more further, the further away that I go, the worse it becomes. So there'll be a limit. And this limit will give me the depth of focus. So the max value of I that allows me to stay within those limits. Okay? And this has to be true for all the values of u comprised between these, okay, my aperture that I'm considering. So that the focus actually is guaranteed, all right, all across the range, but also the door. Or if you want, the azimuth. So, if I rewrite this, okay, and I put the maximum value of u, which is here L, okay, maximum value for I, okay, this is just some mathematical manipulations, but if I put maximum value of I as delta R divided by 2, so that delta R sits across this point B, so that's delta R. The delta R divided by 2 represents the maximum distance, okay, either way. So if I replace that, okay, then I have to constrain it to be less than pi divided by 2. Then I do another mathematical passage here. And then what I found out is the delta y, okay, must be less than this maximum value that gives me pi divided by 2 in terms of phase rotation, which becomes equal to this value here. And that is for the range Doppler technique. So that means, okay, that now my depth of focus can be calculated based on this system parameters here. Right? So now I can figure out how big this can be. Then we'll do some examples with numbers and get a grasp of how much they can be. And I can do it also for the coherent integration technique, which actually it coincides with this when Ls is equal to 0. So if you put Ls equal to 0, you do the calculation. Then you end up with a constraint for the coherent integration technique. So you got, for the two techniques, you got two different depths of focus. Fine. Question, what happens when the swath width is greater than depth of focus? Well, if you find out that your swath, okay, X amount of kilometers, is bigger than the depth of focus, which usually is, then what you can do, you can, you know, subdivide your range cells in batches that are, okay, all of dimension that is less than this depth of focus. And you go now and reprocess your data with, without having to calculate this phase term here for each range cell. But you do it, okay, for each of these points, which represent the central point of each of these swaths here. So you do it in batches, yes.
So you're pretty much choosing your focus point in that, yeah.
In batches, so that now you know that if you focus with respect to this point, all this image in terms of range and azimuth will be well focused. And you go on like this. Here is an example with a ERS-1. This is a spaceborne satellite, a pretty old one. But just to give you an example, so if you put numbers in, what happens. This satellite system had an antenna that was 10 meters long in azimuth. So that was 5 meters resolution of the ground. The operating frequency is 5.3 gigahertz. It's a C-band type of radar. So the lambda was thus 6 centimeters. And the incident angle is 23 degrees for ERS-1. So the depth of focus for this particular one here, see, it's 8.531 kilometers. The total swath for this system was 100 kilometers. So you quickly calculate this, and you need 12 sub-swaths to form the whole image without losing the focus. Unfocusing condition. What is this? So again, you've got this phase correction term here, okay? And we want to now investigate what happens if we don't compensate at all. All right? That is called unfocused SAR. So I want to know what happens if I form my image without performing motion compensation. So I basically neglect that. And now I'm looking for this phase rotation of, again, pi divided by 2 that is induced by this term here, which I'm not focusing anymore now. So I'm looking over I and U, okay, particularly U, to try and understand now, so I can do this for each I, to understand how far I can go, okay, without focusing the image. And I'm searching over this term here. So if I write this, okay, and I search for maximum value of U, okay, this gives me, right, the value of the extension of my image in azimuth that will be still focused even if I don't perform this motion compensation. And this, if I apply this, okay, for the maximum value, which now becomes a function of this parameter here, and then I find out that this parameter L prime will have to be less, okay, than the square root of the product of R0 times lambda. So this tells me that I now can focus over an image, okay, size that is determined by this L prime. This L prime could be, if it's greater than L, okay, which could be, then limits my size of the scene that I can obtain that is still focused without performing motion compensation. Okay? And that's the so-called unfocused SAR. And unfocused SAR actually existed in the past. It's been used. Okay? And that was at the time where computational power was a problem. And they didn't have any means to perform motion compensation. Let's have a look for the, again, same, yeah.
So if we just think about it, you've essentially got these chirps, each target serving to chirp, you're taking it to that, so you're giving these like ribbed shapes. Like, is this condition basically saying how thin can that rib be?
Exactly. Okay. That's exactly it. So that limits my aperture to a point where it might even shrink down to being just one element. You know, with one element, of course, you don't get anything focused. Then you get 2, 3, 4, 5, 10. At a certain point, it would break it.
Thank you.
No worries. Yes.
Is there a hard limit to the amount of motion compensation you can
Nowadays, no. This is the original stuff. But it's interesting to see because then we'll talk about ISA as well, and we'll see how much these things are correlated. Anyway, let's look at the again the same space-borne SAR, right? So same parameters. Okay, that was flying at an altitude of 780 kilometers, and we now assume that LS is 0 coherent integration to K. Right? So if we assume that now, we imply this condition. So we apply this condition here, right? So if we apply the condition there, what we're trying to understand here is what the resolution would be with the maximum value of L that we can tolerate. And if you look at the maximum resolution that you will obtain, it's 112 meters. So that tells you the value of L will be so short that now your resolution on the ground is 112 meters, which is not good enough. But if you apply the same thing for an airborne SAR, you can see that for an airborne SAR, all right, with these parameters here, and again, this is even flying quite high, you can even get better than there. So you get a resolution of 12 meters, which is not a great resolution, but it's not too bad. So with an unfocused SAR, for an airborne SAR type of system, you can still use unfocused SAR. Still buys you something. Again, nowadays there's no need to do that. We've got so much computational power on board that we can actually form images with centimeter resolution. So this is something that was happening in the past. But if you don't know anything about SAP, you don't know how to do motion compensation on a fly, you get something. Maybe without processing at all, just get something. Which is, of course, not optimal because you can do much better. But it's interesting to see that you can get some things out of it. So even with just simple collected data from radar, okay, you just apply your FFT, and you get if you don't extend your aperture too much, you can get a nice image of the ground. I mean, poor resolution, but you can still recognize things, even without applying any SAR processing or FFT. Which is interesting because it's something you wouldn't expect necessarily, but it happens up to a certain point. And then we look at range migration as well. Okay? And then we have a break. Range migration. What's range migration? Well, we have ignored this so far. But range migration is a problem because as you fly by, okay, a point on the ground doesn't stay in the same range cell all the time. And why so? Because of course the distance changes from the furthest point to the closest point. If that distance change, all right, is greater than your range resolution, that means that your point on the ground will migrate from one resolution cell to another. And this shows you, see, the sample at point O as it moves in distance depending on the position of your scanner, of your antenna element. And this, this curve here, right, follows exactly that rule that we've seen before. But so far we ignore the fact that it was leaving the range cell. In fact, we have processed the signal as if that was always present in the same range cell. So there must be some condition that tells me, okay, you are in a condition where range migration is not occurring, or in the condition where range migration is occurring. Okay, so this is the approximated version, okay, of the actual range migration. And this is, again, our Taylor expansion, stop the second order, which is quite good up to certain approaches. So if we consider that, now the range migration condition, see here, which is the distance between point O at the minimum distance and at any time, at any space U, and if you take the maximum value of U, then you get to the maximum distance. So if you do that, okay, and U becomes L divided by 2, so you get L divided by 4, squared divided by 4, times 2, and you get this term here, right? So now what I want to use as a limit is this term here to be less than a percentage of my resolution cell. I may put this alpha even equal to 1 if I want, but that would give me a total loss in terms of energy, right? Because as the scatter migrates, right, what happens is that I don't lose it abruptly when it changes the resolution cell. As you know, the response, okay, of my range profile is still made of string functions. Even if I use a chirp or whatever, it's made of string functions. So that means that I start losing power coming from that as the say the point moves out of my range cell. Oh, now this 0.2 is a very strict. We can relax that at any time. But if you really want it to be strict, you should consider an alpha value too. It's very strict, but we show that this is the condition, there's absolutely no range migration that affects our results and our performances. So if you do that, right, you end up with this condition here, which of course limits your aperture. So you can find your aperture limitation based on these parameters here, okay? Based on the range resolution you got, the minimum range, because of course you get the worst result at the minimum range, okay? And then basically you get this restriction on your aperture length. So then basically limits your aperture maybe only to this point here, when your range of migration, see, only changes the position of your scatter by at 0.2 times the range. So 20%. That means you only allow 20% motion of this point within a range. Okay? So that basically what this says. So this distance here is the distance between this and there, right? So what you're doing here is you're trying to make sure that this distance is less than a certain percentage of the range resolution, which results to this expression here, where now if you invert it, you get a constraint for L, which is the aperture. Okay, few numbers here. Yeah, but this is just a way of expressing these numbers. This stuff that you've seen already. Okay, so delta range is C over 2b. This is just to express those parameters here in terms of system parameters. Okay, so delta R becomes C over 2b, where b is a system parameter. Delta x, okay, this is calculated as ds divided by 2, which becomes system parameter. L is actually RP times theta azimuth, which is the footprint on the ground, and you can also calculate that in terms of system parameters, okay? And Rm, again, you calculate it as system parameters here, which is the minimum distance. I'm not changing things, I'm just replacing these. These are not system parameters, right? These are, well, the delta R is, but I can substitute it with the bandwidth, which is something that, from a radar point of view, is directly seen as a system parameter. And Rm, of course, is a geometrical parameter, but I want to relate this to system parameter in the sense that now I know what my swath is, I know my incident angle, and I know my altitude. So these are all parameters that I directly relate to radar. Where I'm pointing the antenna, how I am flying, and what the swath is. So these are, so if I rewrite this in terms of this parameter, right, this comes out to be example of this. Nobody tells you that you can't use this. You have to calculate them though. And to calculate this, you still have to use this factor. One way or the other. This is more compact, if you want, but then you have to calculate these parameters. Otherwise, you just plug in all your system parameters and find your solution. Once you have this written in MATLAB, and you change the system parameters and you get different results, right? Anyway, as an example, again for the same spaceborne SAR system, if you look at the condition here, see, right? That's alpha. If you calculate all these terms here, given this system, all right, this is a fixed system with set parameters, you end up with 0.38. So you got a 38% migration, which, for example, if your condition was to be less than 0.2, then you would straight away say that the S1 is gone, range migration. It is a light range migration. It's not so severe, but it can affect a little bit of performance. So you might want to go with some range migration correction there. You have to use other algorithms. But it can go away without doing it and still not lose too much in terms of performance. So as you can see, this system here was designed in a way that it didn't need too much processing. Okay, and this is not too old. That is not one of the first. It I think was launched in the 90s. Okay? So it's not too old. It's oldish, but not for me. Anything. Okay. Right. What's the time? Let's see if we can take a break now or later. What's the time? Shall I take a break? Yeah. After this, we're gonna. I know it's a lot of stuff, but now we're gonna do some sort of a tutorial. I'll give you some parameters.